Hello everyone and welcome back to Introduction to Number Theory. This time we will introduce Pythagorean triples. Well, Pythagoras' theorem in geometry is perhaps the most famous mathematical theorem in the world. And in number theory, by Pythagorean triples, we call triples of positive integers a, b and c, which satisfy the Pythagoras equation a squared plus b squared equals c squared. And I'm sure that many of you know several such triples, so let's consider examples of such triples: 3, 4, 5, or 6, 8, 10, or 5, 12, 13. You may notice that we can take a Pythagorean triple and multiply all three numbers by 2, by 3, by 4, and so on, and obtain new and new Pythagorean triples. So if we know at least one Pythagorean triple, for instance 3, 4, 5, then we can obtain infinitely many Pythagorean triples. However, all these Pythagorean triples are similar to each other. And we can notice that besides the triple 3, 4, 5, there exists a triple 5, 12, 13, or 8, 15, 17, or for instance 715, 1428, and 1597, which are mutually prime. They're pairwise mutually prime. So the question is whether there are infinitely many such mutually prime Pythagorean triples, so-called primitive Pythagorean triples. And we will soon see in one of the next videos that there indeed is an infinite set of mutually prime primitive Pythagorean triples. What's more, we will obtain formula for all such triples. So in some sense we will solve this equation in the set of positive integers. We will solve this Diophantine equation. But in this video I would like to discuss some properties of all Pythagorean triples. So let's proceed to the properties. Well, first of all, you may notice that at least one of the numbers a, b, or c is divisible by 3. Well, why is this so? The square of an integer gives remainder 0 or 1 when divided by 3. So if we suppose that none of them, neither a or b or c, is divisible by 3, then all three squares should give remainder 1 modulo 3, which means that the Pythagoras equation modulo 3 would look like 1 plus 1 equals 1, which is of course not correct. So from this it follows that it is impossible that none of these numbers a, b, and c is divisible by 3. The second property is about divisibility by 4. And in order to prove that at least one of them is divisible by 4, we need to consider the remainders of their squares modulo 8, not 4. Well, you may already understand why modulo 4 is not enough. If we find an element of Pythagorean triple whose square is divisible by 4, then this would only mean that this element of Pythagorean triple is even, but not necessarily divisible by 4. However, if we prove that, for instance, a square is divisible by 8, then a must be divisible by 4. So let's consider remainders of squares of integers modulo 8 it's easy to check that only 0, 1 or 4 could be such remainders. So if we suppose that none of them is divisible by 4, this would mean that none of the squares gives remainder 0 when divided by 8. So in the Pythagoras equation, we will have to use only 1 or 4 modulo 8. And by checking several cases, it's easy to see that the Pythagoras equation cannot hold if 0 is forbidden modulo 8. Well, for instance, 1 plus 1 is not equal to 4. It's either not equal to 1. 1 plus 4 is neither 1 or 4, modulo 8, of course, and so on. So at least one of them, at least one of the integers a, b, and c must be divisible by 4. And of course, the last property in this video is about divisibility by 5, and we will show that at least one of a, b, and c must be divisible by 5. Of course, considering remainders modulo 5. Once again, we see that possible remainders of squares modulo 5 are 0, 1, and 4. And if 0 is forbidden, then we need to use 1 and 4 to form Pythagoras equation, which is not possible. We just check several cases and understand that it will never hold. So at least one of the numbers a, b, and c must be divisible by 5. These are the three perhaps simplest properties of Pythagorean triples, and I invite you to the next video where we will discuss general formula for all Pythagorean triples.